calculus. Welcome back. So 6-5. This is the last section that we do in chapter 6. Teddy, will you just take a minute to make sure it's zoomed correctly and everything? Okay, all right.
Yeah.
So 6-5 is entitled the average value of a function. Okay, and 6-5 compared to 6-2 is like comparing, okay, I'm not going to make a very good analogy here. Maybe if 6-5 is a small mound of dirt, then 6-2 would have been, say, Mount Olympus. Okay, 6-2 takes a whole lot more conceptual understanding. It takes a lot longer to understand 6-2 than it does 6-5. So we can do, I think we can understand 6-5 after only one problem. And I'm not going to do a problem yet. I want to just talk about the concept of the average value of a function. So I'm drawing a function, we'll call it f of x up here. And we'll identify an interval on the x-axis. Teddy, make sure you can see that, okay?
Yeah, I can see that.
Okay. So the function f of x on the interval from x equals a to x equals b, if you notice, it takes on a lot of different values, okay? Like its value here at a is smaller than its value is right here. It looks like that's about the highest that function ever goes on the interval from a to b. And since the value of f of x is continuously changing on the interval from a to b, really f of x takes on an infinite number of different values on that interval. So to think about the average value of f of x on ab, well, conceptually, it makes sense to think about it as, well, I can take the average of all the values, find all the different values of f of x on AB. But if you think about it, if f of x takes on an infinite number of different values, to find the average, I'd have to add up an infinite number of values and then divide by infinity, okay, which obviously is not going to happen. You can pass through, revise, that's fine. Okay, so a conceptual way to think about this is, well, I can tell that the average value is, it's going to be higher than the function is right here, since that's the lowest point that the function ever takes on. It's going to be lower than the function is right there, because that's the highest point that the function ever takes on. The average value should be somewhere maybe somewhere in the middle, maybe like around there. Okay, I probably don't have that drawn very well. That black segment that I drew probably should be a little bit higher. It looks like there are more values above that black segment than below the black segment. But a good way to think about it maybe is to think, okay, if f of x were a frozen wave and we melted that water, and so it was no longer frozen into a wave shape, it would just, the top of the water would end up being flat. And however high that water was above the x-axis, that would be the average value of the function. Okay. Well, okay. So how are we going to compute that? Well, I know that I can find the area under the curve, the area between f of x and the x-axis, by integrating f of x. Okay. And I know that area under the curve should be the same as the area of the rectangle formed by the x-axis, that black segment at the top, and then the two vertical segments at x equals a and x equals b on the sides. The area under the curve should be the same as the area of that rectangle. Okay, so this, when we were developing the fundamental theorem of calculus, we actually kind of talked about this a little bit. But what we'll do here is, I know that the area of that rectangle is going to be, the length is b minus a, and the height is some quantity, I don't know what it is, but whatever it is, it's the average value of the function f of x on the interval from a to b. So I'm going to write this as f that's b minus a is that, it's the length of the rectangle. And then the average value of the function, that's the height of that rectangle. And I know that that area, length times width, should be the same as the area between the curve f of x and the x-axis from a to b. So that's f of x, the integral of f of x dx from a to b. So then I have an equation there that's definitely true. That says that the area of the rectangle, okay, is equal to the area under the curve, okay? And now, so I have f average, the average value of f of x on the interval from a to b, is represented right here. So to get a formula for that, I just divide both sides by b minus a, and I get f average equals 1 over b minus a times the integral from a to b of f of x dx. So that is essentially the formula that we can use to solve really any problem in 6-5, and anytime that I want the average value of a function. If I have a function that represents the velocity of a vehicle, okay, and I want the average velocity on a time interval, well, I just integrate the velocity function over the time interval and then divide by however long the time interval is. Okay, so let's do that. Let's maybe do a problem with this. I'm gonna. This is actually problem number 1 out of the assignment. If you want to pause the video and open your assignment, you can play along. But it gives us a function f of x equals 10x minus x squared, and it wants us to find the average value of that function on the x-axis interval from 0 to 2. Well, I mean, I don't have to draw this. I don't have to really do any thinking at all. Okay, I'm trying to find the average value of f of x on this interval. I know that I can go straight to the formula. The average value of f here will be 1 over the interval length, which would be the distance from 0 to 2 is just 2, times the integral from 0 to 2 of 10x minus x squared dx. Okay, and of course, now this problem, I'm looking at the box and it doesn't say to round to any particular decimal place. If it did, I could just type this expression into my calculator and integrate it on my calculator, but it looks like I'm going to have to do the integration by hand here. I may or may not finish the integration. This would be 1/2 times, now I'll get the antiderivative here, 10x squared over 2 minus x cubed over 3, evaluated at 0 and 2. And then, I would simply have to substitute 2 in, so that's 1/2 times, let's see, 5 times 4 is 20, minus 8/3, okay, and then minus, I guess it all goes to 0. So yeah, essentially that would be 10 minus 4 over 3 once I multiply the 1/2 through there. A half of 20 is 10, and then a half of negative 8/3 is negative 4/3. So that gets you to your answer pretty quickly. So I don't necessarily think you're going to have much problems, many problems doing 6-5. It's quite simple. You're just finding the average value of functions. I'll tell you how we do it time-wise there, boy.
8 minutes, 9 minutes.
9 minutes, okay. Yeah, so what I wanted to do, and I sent you an email this morning about doing a practice exam. I linked to the 2018 calculus exam. Listen, for the two of you who are going to take the AP exam in May, I highly suggest if you just Google AP Central, AP Calculus, AP Central, something along those lines, you can get to all of the released questions very easily. And I would highly suggest that you start doing those. If you read, I think I mentioned it in a video, or if you've read the information that I linked to you about the AP exam, particularly for this year, there's not going to be any solids of revolution on there. Okay, but there is something that's going to be on there that we have not talked about yet. And that topic is differential equations. And so that's what I'd like to at least begin right now, is kind of a discussion of differential equations. There are very limited types of differential equations on the AP syllabus. in particular, beyond just the extremely simple differential equations, which is the first one I'll talk about. The only other type are called separable differential equations. So let's just start. What is a differential equation? Well, a differential equation is an equation that contains at least one derivative in it. Okay, I can write a differential equation right here. Dy by dx, there's a derivative, equals x squared. That, friends, right there is an extremely simple example of a differential equation. It's an equation because it has an equal sign in it. It's a differential equation because it contains at least one derivative in it. Now, that differential equation could just as easily be written as y prime equals x squared. You guys know that means the same thing as what I have written here. Okay, so that's a differential equation. Now, let me explain what the solution to a differential equation means. Okay, there are actually two different, very distinct types of solutions for a differential equation. The first type is called a general solution. Okay, and we'll do that first. And what a general solution to a differential equation is it's a family of functions, all of which satisfy this differential equation. Okay, so it's a family of functions. Okay, functions of, in this case, x. Okay, and all the differential equations that you'll see, the solutions will be functions of x. So to get a function of x for which this is true, quite simple. All I have to do is, to get a function of x would be denoted as y. Y equals some expression in terms of x. All I would have to do to turn this into a y is, well, this is the derivative of y with respect to x. So to get y, I would just have to take the antiderivative of this, or another way to say that is a slightly less correct, but equally usable way to say that is to say I'm going to integrate this with respect to x. Okay, remember that differentiation and integration are inverse processes according to the fundamental theorem of calculus. So what I'm going to do is I'm going to integrate that expression with respect to x. Now, going back to Algebra 1, we know that if I perform an operation on one side of an equation, I have to perform exactly the same operation on the other side of the equation. So if I'm going to integrate this side, I'm going to have to integrate the right side as well. Okay, and that's exactly how you show it. Well, the antiderivative, or the integral of the derivative of y, must be y. So this side, the left side, becomes y, and then I've got to integrate this side with respect to x as well. Well, that's a simple antiderivative. That's x cubed over 3, and then of course, all right, we add plus c, okay, because the integral of x squared could be this function, or it could be any function at all that differs from that function by just a constant. Okay, so this is actually the general solution to that differential equation. That's all there is to it. Okay, so what I want you to understand just from this, a differential equation is an equation that contains at least one derivative, and the differential equations that you'll see will always contain exactly one derivative. Okay, to solve a differential equation, we're going to anti-differentiate. Another slightly less correct way to say that is we're going to integrate. Okay, or a slightly less precise way. It's still correct. It's just less precise. So I integrate this side. The integral of a derivative is the original function. Okay, the derivative of y is dy by dx. So the integral of dy by dx is y. And then I integrate the other side as well to keep the equation balanced. That's a simple antiderivative, and of course it's an indefinite integral that I have written over here, so I have to add plus a constant. All right, so that and then the general solution of a differential equation looks like this. It'll always have a plus a constant at the end. Okay, now let's talk about a particular solution. Now, the second type of solution that you'll see is called a particular solution. And the particular solution to a differential equation won't be a family of functions that satisfy the original equation. It will be one specific function that satisfies the original differential equation. So I am going to, and to find a particular solution to a differential equation, I don't have enough information up here to find any particular solution to this differential equation. I need another piece of information. I have to know at least one pair of values that would exist on the solution function. Okay, here's maybe a better or simpler way to say that. I have to know the value of y for one particular x value. For instance, a problem might say, okay, here's a differential equation, and find a particular solution for this differential equation for the case where f of 0 equals 2. Okay, so I'm supposed to find the function that satisfies this differential equation, and it's got to pass through the point 0, 2. When x is 0, the y value on this function has to be 2. Okay, well, I start the same way. Okay, I start the same way by finding the integral of each side. So that's going to be y equals x cubed over 3 plus c. And that's the general solution right there. But, okay, here's what I do now. I'm going to use this set of what we call initial conditions, okay, to figure out the value of c for this particular solution. Okay, so then, if I have an actual value for c instead of just the letter c, that means I'll have one function rather than in a family of an infinite number of functions. So let's do that. And all I have to do is, well, I know that f of 0 has to equal 2. So I know that when x is 0, y is 2. So I'll substitute 2 in for y. I'll substitute 0 in for x. And notice that term goes to 0, so all I have left is 2 equals c. So c ends up being 2 here. And now that I know that c is 2, I know that I can take this general solution and turn it into a particular solution by replacing the c with a 2. So I get y equals x cubed over 3 plus 2. And that is the particular solution to the original differential equation for the initial conditions f of 0 equals 2. Okay. Initial conditions could also just be given as an ordered pair. We could say, the solution to this, the particular solution to this differential equation has to pass through the point 0, 2. Okay. That's the same information as is given here. It just could be presented differently. Okay. Teddy, how are we doing time-wise?
You're doing 18 minutes.
18 minutes, okay. Listen, much more on differential equations here in a minute, and I'm going to do the next video right away. This type of differential equation, honestly, you could have solved without any help from me. But, like I said, we are going to learn a specific type of differential, how to solve a specific type of differential equations. We'll do that next time. Thanks for watching.